Today, we're diving into one of the greatest scientific detective stories of all time. It's about how two forces of nature we thought were totally separate, electricity and magnetism, were suddenly revealed to be two sides of the same coin. This is the story of James Clerk Maxwell, a story of hidden clues, a deep, nagging puzzle, and a final revelation that literally changed the world. Let's get into it.
And hey, don't just take my word for how huge this was. That's a quote from Albert Einstein himself. A whole generation later, Einstein basically said, yeah, my theory of relativity, it started with Maxwell's equations. That's the level of impact we're talking about here. Absolutely foundational.
So here's our roadmap. We'll start back when electricity and magnetism were complete strangers. Then we'll look at the first clue that brought them together. We'll see how that connection actually created an even bigger puzzle, and then watch the stroke of genius that solved it all, leading to an incredible discovery about light itself.
Okay, so let's set the scene. Before the 1800s, if you were a scientist, you treated electricity and magnetism like two totally different things. You just didn't mix them. They had their own rules, their own phenomena, and they lived in completely separate worlds.
Think of it like this. You had electrostatics over here, which was all about static electricity, rubbing a balloon on your hair. And then you had magnostatics over there, which was about bar magnets and compass needles. They each had their own set of laws, their own physics. They were like neighbors in the textbook. But as far as science was concerned, they were on different planets.
And then, in 1831, everything started to change. This is thanks to the incredible work of Michael Faraday. He found the first real solid link between these two forces. And honestly, it kicked off a revolution.
And here it is, Faraday's law of induction. The key word, the absolute game changer, is changing. What Faraday figured out was that a magnetic field that changes over time could actually create an electric field. It wasn't just that they existed in the same universe. For the very first time, we saw one directly causing the other.
And this isn't just some dusty old theory. It's the reason our world works. You see those big gray cans on power poles? Transformers? Their entire job is to use a changing magnetic field to create electricity. This discovery is, quite literally, powering your life right now.
Okay, so huge breakthrough, right? But here's the twist. When scientists took Faraday's amazing new law and added it to the equations they already had, it broke something. It created a deep, fundamental problem. A flaw was hiding in the math. To get what went wrong, you have to know about one of the most basic, non-negotiable rules of the entire universe, the conservation of charge. It just means that you can't create electric charge out of nothing, and you can't make it disappear. The total amount is always constant. It's a hard and fast rule.
And this was the fatal flaw. Now, don't get bogged down by the symbols here. Just focus on what it means. When everything was steady and stable, the laws worked just fine. But the moment you had something changing, like, say, charging a capacitor, the equations predicted that electric charge could just vanish into thin air. It broke that non-negotiable rule. The theory was fundamentally broken.
So, just imagine the situation. The best, most complete description of electricity and magnetism that humanity had violated a core principle of reality. Physics had a serious crisis on its hands. There had to be a missing piece to the puzzle. But what was it? And this is where our hero, James Clerk Maxwell, enters the stage. He looked at this mess of inconsistent equations and came up with an idea that was just, well, it was breathtakingly brilliant. Maxwell's genius was all about symmetry. He thought, okay, Faraday showed us that a changing magnetic field creates an electric field. Well, what if it works the other way around, too? He proposed that a changing electric field must also create a magnetic field. He called this idea the displacement current. And this is how he fixed everything. Again, don't worry about the symbols. Just look at Ampere's law. Maxwell suggested adding just one little term. That part right there. That term is his displacement current. And with that single, beautiful, elegant addition, poof, the contradiction vanished, charge was conserved, the theory worked, he'd fixed physics.
And with that last piece of the puzzle clicked into place, Maxwell gave the world the grand finale, a complete, consistent, and totally unified theory of electromagnetism, all summed up in 4 beautiful equations.
And there they are, in their final glorious form. These 4 equations could now describe every single electric and magnetic thing that was known to exist. Static cling, lightning, the Earth's magnetic field, the motor in your blender, it's all in there. One theory to rule them all. So what's the story these four equations tell together? It's a beautiful, symmetrical dance. The first two laws describe the dance itself. A changing B field creates a swirling E field, and a changing E field creates a swirling B field. The other two laws give us the ground rules for the dance. Electric fields start on charges, but magnetic fields always loop back on themselves, which is why you can never find a magnet with only a north pole.
But the story doesn't end there. Not even close. Because after Maxwell fixed the laws, he realized they were predicting something that no one, and I mean no one, saw coming. Something profound.
Maxwell looked at that dance, a changing electric field making a magnetic one, which then changes and makes an electric one. And he realized they could become a team. They could sustain each other, chasing one another through empty space forever, as a self-propagating wave.
So, naturally, he asked the next question. How fast would this wave travel? He took the fundamental constants of nature, numbers you could just measure in a lab for electricity and magnetism, and he plugged them into his equations. He did the calculation, and it spit out a speed, this speed.
And this was the mind-blowing part, the punchline of the entire story. That number wasn't random. Physicists at the time knew it instantly. It was the measured speed of light. It was a perfect match. It just couldn't be a coincidence.
And in that moment, the truth was revealed. Maxwell had proven, with mathematics, that light is an electromagnetic wave. And not just the light we see with our eyes. As we soon discovered, radio waves, microwaves, infrared, X-rays, they're all just different flavors of the exact same thing. Maxwell didn't just unite two forces, he united them with the entire science of optics. It was breathtaking.
Maxwell's unification of these forces is truly one of the greatest achievements in the history of human thought. It paved the way for radio, television, and all modern electronics, and it inspired the next 100 years of physics. And it leaves us with one heck of a question. What other connections are still out there, hiding in plain sight, just waiting for the next Maxwell to discover them?